So it is 9:15. Very good morning to you all. Today we will continue with our syllabus. That is, today we will be discussing about modeling. So usually students ask me a question, sir, can you give me model question paper or model problems? Why? What do you mean with the term model? Why do we require model? So let us see the importance of modeling everything in the context of control systems. So why we require model? So as explained in the previous lecture, this is a typical block diagram of a closed loop control system. So you have to achieve a desired response. You have to achieve desired output response by using controller, actuator, and by sensing, by using the feedback and all. So how do you do it? You will do it randomly. You cannot do it randomly, right? Or else you wanted to achieve a task, then you will first build a something, some plan, then you build a sensor, then you will build a controller, then you build an actuator and everything. Then you put to see that it is not. Finally, when you club everything, you see that it is not working. So before actually designing a controller or just before arriving at some conclusion or before working on the actual process, what we do is first we try to develop model. So once you have the model, it will be useful for analysis, design of the controller, and you can do the simulation in software and then implement in real time. And if the result doesn't match, then you know where things are actually going wrong. It will also help you to troubleshoot, or it will help you to tell what are the assumptions you made and what assumptions have to be considered seriously, or which assumptions fail us, like that. So that is why we require model. By model we mean mathematical representation of the plant. So model will be useful in the analysis of the system. What it does is it captures the dynamics of the system. So by dynamics we mean that, say for example, if you have a RL network, it is a first order RL circuit, it's a first order system. So you will come to know that if you apply a step input, it exponentially rises to the steady state value. So you know its time constant, how it is varying. Similarly, a second order system will underdamped second order system will have oscillations, it will have overshoot, and critically damped system will not have overshoot. Overdamped system will have it will not have overshoot, but it will It is sluggish in nature. So it captures the dynamics of the system. For quick feedback, am I audible? Is my voice clear? Yeah, thank you. So different ways to obtain a model. These are interesting colors. One is black box modeling, another is white box modeling, another is gray box modeling. So first we will start with black box modeling. As the name indicates, you don't know what is there inside. Black box means what is there inside you don't know. You apply an input to the system, you get an output to the system. So you apply input. From this input output data, you try to obtain a model of the system. So you may do it for various inputs and various outputs. You will get the data. From this data, you will be able to obtain the model of the system. It is also called experimental modeling. So since you don't know what is there inside the system, what components are there, only access you have is you will be applying inputs, you will be observing outputs. From that you will be fitting a model or you will be obtaining a model. So that is why the term black box has come into picture. White box modeling on the other hand is you know every details of the model of the system under study. While obtaining white box models, you know every details of the system. What is there? You know the governing laws like Kirchhoff's voltage law. You know the other laws like Newton's laws of motion. So by applying those analytical laws, physical laws, you will be writing the differential equations governing the system of each element, of each component of the system. Finally club them and make it in a suitable form. That is why it is called white box. You know entirely of what it is. So finally gray box, which is a mix of, it is a hybrid approach of both black box and white box. Say you know what is there inside, but you don't know its parameter value. Say suppose you have RL network, you know by applying KVL you know what is the differential equation, V is equal to IR plus L di by dt. But you will be finding out the values of L and R from the experimental data by applying some known inputs and by measuring outputs. So gray box is an hybrid approach. It is a combination of both black box and white box modeling technique. So what are the types of models? There are two types of models, that is transfer function model, which is applicable for linear time invariant systems. The second types of model are state space models, which are more general in nature. So next we will be studying about elements of modeling. Like you have electrical system, what are the basic elements of electrical systems? What are the basic elements of mechanical systems? What are the basic, finally in tomorrow's class we will be deriving the transfer function of DC motor in armature controlled motor. So we will try to obtain the transfer function of electromechanical systems. So what are the basic elements of electrical systems? You know already resistor, inductor, capacitor. You know the law is V is equal to IR, V is equal to L di by dt. For capacitor, I is equal to C dV by dt, or V is equal to 1 by C integral I dt. So have you heard about this term memristor anytime? It is called memory resistor. So it is a typical nano. You will be able to observe such phenomenon in microscopic scale. So this is of a recent development in the sense maybe from 2000. You can just simply type memristor and you will get some information regarding that memristor. I think everybody knows resistor, inductor, capacitor, but memristor, if you are not here, you can just go through about it, but we are not covering it in detail here. So for mechanical systems, for linear translational motion, the basic building blocks are mass, spring and damper. For rotational systems, mass is inertia, mass is represented in terms of inertia, and spring is torsional spring. The system variables for mechanical system are force or torque, or the angular displacement or linear displacement. So we will be discussing the analogy between electrical and mechanical systems. First one is the force voltage analogy and second one is force current analogy. You have a spring mass damper system. So the governing Newton's second law of motion, it says that force is mx double dot plus bx dot plus kx. M is the mass, beta is the friction coefficient and k is the spring constant. So you have this spring mass damper system is analogous to series RLC circuit with a voltage source. Based on the KVL around the loop, V is equal to L Q double dot plus R Q dot plus Q by C. This also I think everybody knows this. So by comparing these two equations, this force equation and this voltage equation, we can say that force is analogous to voltage, mass is analogous to inductor, friction coefficient is analogous to resistor, spring constant is analogous to 1 by C, and finally displacement is analogous to charge Q. So why do we do this? Why we are going for analogous studies? See, in earlier days, this is a simple system, spring mass damper system. You had a complicated mechanical system. Then for it, you will not be able to apply inputs, or it is difficult to do experiments on it. If it's difficult to measure force, or if it is difficult to measure displacement. But so in olden days, when computers were not in place or such thing, when electronic realization through electronic components was easy, so what they do is they work on the analogous electrical system. They will develop an analogous electrical system for a given mechanical system, and there they will, because the nature is same, they do. If you have an analogous electrical system, you can apply whatever voltage you want and you can measure other variables of interest easily. So in a complex situation, if you have an analogous electrical system of a mechanical system, analogous electrical system for a mechanical system, you will be able to study the behavior of the system easily. So next we will see the force current analogy. Here there is a mistake, slight mistake. It should have been KCL. KCL at node should not be based on KVL around the room, it should be KCL at node. So same thing, spring mass damper system. Now your force is analogous to the current source The moment you use current source, you will go for parallel realization. So R, L, C are in parallel. If you apply KCL at this node, then I is equal to C phi double dot plus phi dot by R plus phi by L. So force is analogous to current, mass is analogous to capacitor, friction coefficient is analogous to 1 by R, spring constant is analogous to 1 by L, displacement is analogous to phi, that is the flux. So did you understand force voltage analogy and force current analogy? You may type understood in the chat box. Phi represents the flux. Voltage is d phi by dt. B is the friction coefficient. Okay, now I have an interesting question to you. So another question is, why gates are more analogous to transformer? Why it is also analog? We can also say that it is analogous to potential divider. Why it is not the case so? So think about this and you can tell. I'm getting few responses, but they are not entirely correct. So think about this and then tell me. Ayush Dilip. May I know what you didn't understand? So gear is analogous to transformer, but somebody is saying gear is analogous to potentiometer. So the question is why gear is analogous to transformer? Textbook gives you gear is analogous to transformer. I got some answer from Vamsi Kishore. In gear system, R star W is constant. In transformer, power is constant. What are R and W? Radius and angular velocity. So think about it. You may think about this question, analogy, you may search the internet uh, and in the coming classes we will try to discuss for a few minutes and before coming to the next class I expect you to revise your Laplace transforms, definition of Laplace transform, and you need to have the table chart showing Laplace transform of all the signals. See, in your mathematics course, you might have studied, or even in your other subjects, you might have studied about solving a differential equation using Laplace transform. So sometimes what I see is in some students try to solve the differential equations using other methods, but in this particular course we will be using Laplace transforms and we will be using transfer functions. So it is very much required for you to revise about Laplace transform and solving ordinary linear differential equations using those Laplace transforms. You just brush up your mathematical basics about Laplace transforms. Once you know it, probably in your circuits you might have found out the Laplace transform and transfer function. So I will formally give all those definition of transfer function, why we obtain transfer function, what is the historical element, like why we are going, and how to reduce the block diagram and obtain the overall transfer function of a closed loop system, how and why we should obtain it, what are the advantages, what are the methods you have to obtain the overall transfer function of a closed loop system. Those things I will discuss in the coming class, but for that you need to brush up your Laplace transform. Now coming to the question,